Welcome to UVU CS3060 Lecture 10.2, where we talk about the performance of demand paging. So understand that demand paging is a wonderful situation if you want to give processes more memory than may physically be available, but there is a price to pay. The performance of demand paging can be actually very, very steep if you don't control it. If you simply think, oh, I'll just simply page everything. Because remember, there are many steps involved when it comes to demand paging. The first thing that has to happen is we trapped the operating system, which means a context switch. The operating system needs to determine that the page fault happened and that it was legal, and that the page that needs to be loaded is on disk. It then goes ahead and performs a disk operation, which means it has to wait in the queue while it waits for the read to happen. Any seek or latency time, the transfer from the drive to the system. Usually, while this is all happening, we context switch to another process so that the CPU can be kept busy. Eventually, the CPU receives an interrupt from the disk saying it's completed, which means another context switch to switch out the running process for the operating system. Then we go ahead and determine what the interrupt was about and what needs to happen. The operating system goes through and changes the page table and anything else, any other data structure that needs to be modified, determines that particular process needs to be put on the ready queue so that it can be launched again, at which point the registers are restored, another context switch, and everything is brought back so that instruction may be run again. So we can see that there are three things that are happening. We have interrupt servicing that happens. This is, again, context switching and can be very expensive. We read the page from the drive, and you'll see that this takes a lot of time. And then finally we have restarting the process, which is, again, just another context switch. So when it comes to calculating the performance of demand paging, we need to consider how many times, or the ratio of page faults to memory accesses. The page fault rate basically is a number that identifies how many page faults there are compared to the number of actual memory accesses. When this page fault rate is close to 0, basically no page faults are happening. But if the page fault rate is 1, this means that every memory reference is a fault, and that's clearly what we're trying to avoid. We'd like to get our page fault rate to as close to 0 as possible. Now the calculation is going to use this page fault rate value and use it very similar to other calculations that you've seen before. When the page fault rate is low, then we're going to see just simply the memory access, which is usually measured in nanoseconds as being part of the calculation. Whereas if their page fault rate is high, then not only are we going to worry about the page fault overhead, which is the operating system swapping in and out, but we also have the swapping of the data from the drive into memory and possibly from memory into the drive if we have to free up a frame. This is the expensive part of the equation here. This is usually measured in microseconds or milliseconds. Remember that nanoseconds is a billionth of a second, microseconds is a millionth of a second, and millisecond is a thousandth of a second. So here's a calculation where we have a memory access time of 200 nanoseconds. This is very fast, 200 billionths of a second. Then we have our page fault service time, which is the time it takes for the operating system to do what it needs to load a page from disk. This is 8 milliseconds. We're talking thousandths of a second. The difference between 8 milliseconds and 200 nanoseconds is extraordinarily large. We've got a huge difference. If you take a look down here, the 8 milliseconds is basically 8 million nanoseconds. So we put our calculation together. We have our memory access time of 200 nanoseconds and our page fault service time of 8 milliseconds. We normalize the units here so that we have 200 nanoseconds of memory access time and 8 million nanoseconds of disk access time. We can see that the equation eventually comes down to p times nearly 8 million. So let's say that 1 out of 1,000 page faults, or 1 out of 1,000 memory accesses cause a page fault. This tells us, based on our calculation, that our EAT, estimated average access time, is going to be 8.2 microseconds, which is a slowdown factor of almost 40 times. This is only 1 out of 1,000. So let's try to get if we want to get our performance degradation less than 10%, well, if our performance degradation is less than 10%, what we would need to do is we'd actually need to have an EAT of 220. So DAT should be 220. Well, to get that value, we need a page fault service time, or the page access ratio here, to be 1 in every 400,000 memory accesses. So you can see demand paging is very expensive, and we really want to minimize this, if at all possible. So how can we optimize this? Well, swap space can be faster than file system if you make the swap space either in large chunks or one large contiguous chunk. Under Linux systems, our swap space is a partition, considered the best way to handle that. Although there are other ways. Windows has one large contiguous swap file. Often, demand paging will try to optimize by copying the entire process into swap space first. Normally, files that are in a file system are not always contiguous, meaning that if you copy the process image into swap space, it will be contiguous at that point because the operating system has complete control over the swap space. You can do demand page from program binary on disk, but what you do is you discard rather than paging out. So if you've got a binary program, there's no modification on most systems where a page is execute only and you cannot write to it. So why in the world would you swap that to disk? You could just simply release that page. And while that does not eliminate the need to read a page, it will eliminate the need to write, thus cutting our access time in half. Now, we call the pages not associated with a file, we call these anonymous memory pages. This is like heap and stack. Usually this isn't swapped in and out, but sometimes it can be. And also, you have to consider pages that are modified in memory but haven't been written to the file system. Again, we talked about this before. Mobile systems typically don't swap. What happens instead, demand page from the file system and reclaim read-only pages like release it, such as the code. Now, there is a concept called copy on write. Copy on write is a very interesting demand paging system where when it comes to a fork, you'll have a parent and a child process that will initially share the same pages in memory, even the writing ones. The thing is, when one of the processes modifies that shared page, then will the page be copied. So memory can actually stay on the shared as long as it's been read-only. And this usually includes the program as well as read-only data. Clearly, copy on write is a very efficient way for creating a new process. So, in general, whenever you allocate a new page in memory that's not just simply going to a file, this is allocated from either a pool of pages or from a page called zero fill on demand. Zero fill is a very interesting aspect where a page is completely full of zeros but is read-only. And that page is assigned to the process. In fact, it's probably assigned to multiple processes. And it is only changed whenever it's written to. So if a process reads zeros, then a zero fill on demand will just simply share that particular frame with all the other processes that may have it. So the key here is the pool should always have a free frame, and if one is not free, or if an allocation is made which takes up the pool, then time is taken to free up a new frame. Now, vfork is another system call that has the parent suspend and the child uses copy on write from the parent, and is designed to have child to call exec, and usually is considered very efficient. So here's what copy on write does. This is before page C is modified. We have two processes that share the same physical memory frame in each of their particular process's memory space. Now in the next diagram, we'll see that page C gets modified by process 1. So process 1, when it attempts to modify C, causes a page fault, at which point the operating system copies page C to a new frame. Then that process continues, is assigned this new frame in its page table, at which point, when the process finishes the write instruction, it will be to this frame where C is located, as opposed to process 2, which process 2 will still point to the original page. In most systems, when the copy on write happens, both the process doing the writing has a new frame assigned to it, and the process that is not doing the writing will have its invalid bit unset so that it can continue with just simple read access. And it can also write, since it doesn't share the page with another process at that point. This brings us to the end of lecture 10.2, where we discuss performance issues with demand paging.